I'm Grant.
I'm Joe.
And I'm Christian, and we're shooting guns today.
Hey, Krister, what kind of gun is this?
Well, it's actually today we're shooting 3 guns. We have the Ruger at 22 caliber with the red dot sight.
We have a Remington 20-gauge shotgun, but it'll be shooting a slug today with a scope. And we've got a Savage Arms 17 HMR with a scope as well.
Go.
I hit it again.
You
No
hit it?
way.
The hole. So how do you think today went?
I think we went pretty well. Good day at the range.
It was.
So what now?
Time to go plug and chug.
Taking the data that we found at the range, we are now going to calculate the final kinetic energy of our targets. Each target, the masses we found for the target of the 17 HMR, the 22, and the 20 gauge were 0.015 kilograms, 0.009 kilograms, and 0.015 kilograms. Our delta X value, or the distance the target traveled after it was shot by the bullet, was 0 meters, 0.0762 meters, and 1.63 meters. Our delta Y value for all 3 targets was 1.08 meters. Our time value we found by using the equation delta Y equals velocity in the Y direction times t plus 1/2 acceleration in the Y direction times t squared. Our velocity in the Y direction was 0 as the targets were sitting still, giving us delta Y equals 1/2 acceleration in the Y direction times t squared. Solving for t, we get t is equal to the square root of 2 delta Y over acceleration in the Y direction. Plugging in the acceleration in the Y direction as 9.81 meters per second squared, or gravity, we get t equals the square root of 2 delta y over 9.81. Plugging in our y values for all the respective targets, we get the time for all three targets to be 0.469 seconds. Our velocity of the target was found using the velocity equation, change in position over change in time. We plugged in our delta x values for each target along with their time values to find their velocity in the x direction to be 0 meters per second, 0.162 meters per second, and 3.47 meters per second. Now we can calculate the kinetic energy of each target using the equation kinetic energy equals 1/2 mass times velocity in the x direction squared. Using our mass values and our velocity values, we find our energy in joules to be 0 for the 17 HMR target, 1.19 times 10 to the negative fourth for the 22, and 0.0905 joules for the 20 gauge target. Given the data that we found on each of our bullets, we are going to calculate the final kinetic energy of each projectile. Our mass and our velocity were given to us in grains and feet per second, so we must convert them to kilograms and meters per second. We found 1 foot equal to 0.3048 meters. Therefore, 2,550 feet per second is equal to 777.2 meters per second. 1,235 feet per second is equal to 376.4 meters per second, and 1,800 feet per second is equal to 548.6 meters per second. Then we found 1 grain is equal to 6.48 times 10 to the negative fifth kilograms. Now 17 grains is equal to 0.00110 kilograms. 40 grains is equal to 0.00259 kilograms, and 250 grains is equal to 0.0162 kilograms. We then went and plugged them into their charts with their respective caliber bullet and calculated our final kinetic energy using the equation 1/2 mass times velocity squared. Plugging in our values, we found the kinetic energy of the 17 HMR to be 332 joules, the kinetic energy of the 22 to be 183 joules, and the kinetic energy of the 20 gauge to be 2,440 joules. To calculate the energy loss between the bullet and the target, we took the kinetic energy of the bullet minus the kinetic energy of the target to give us the entire energy lost. Taking each K sub B and K sub T value and subtracting them, we find the energy lost in the 17 to be 332 joules, the energy lost in the 22 to be 183 joules, and the energy lost in the 20 gauge to be 2,440 joules. However, we did notice that with an increase in mass of our projectile, there was an increase in energy in the target. Increasing our mass from 0.0011 kilograms with the 17 HMR to 0.0162 kilograms with our 20 gauge, there was an increase in energy of our target from 0 joules to almost 1/10 of a joule of energy.